All right, guys, good afternoon. Let's start with today's class. In today's class, we are going to go over the concept of energy. So there are three forms of energy that we are going to be using in this unit, in this chapter. The first one is the one I introduced at the end of last class, which is kinetic energy. So kinetic energy is the energy related with motion. So if you have a mass which is moving by this force, and it has an initial speed vi, then because of the force, it's going to accelerate, right? So using differentials, we have to work. We know work is force times displacement or force times distance, but we can write it like this. dW, the differential of work, is F dx, right? This is the x-axis. So force is mass times acceleration. Now, acceleration is velocity over time. Now, analytically is dv over dt, the derivative of velocity in respect of time. So we basically just plug this there, here, and then we have to integrate on both sides. What happens is that position versus time, or position of dx dt, is v. So you have this integral, which basically leads you to this equation here, right? So the takeout from this is that the kinetic energy is 1/2 mv squared. That's the main thing. Now this is just a proof, right? You can prove using work that kinetic energy is that. So there is a direct relationship between work and energy, right? Or in this case, kinetic energy. The work by the external force is what gives you that kinetic energy on the mass, increases the energy on the mass. All right. The other form of energy that we're going to be using a lot is potential energy. So for that, we are going to place a mass above the ground. And we know that if we let it go, because of gravity, the mass will fall towards the ground. Now, the distance is y from the mass to the ground, and the force of gravity is drawn here, like that. So, just like here, we write work or differential of work negative mg times dy. It's a differential of displacement. That will be dy here. Doesn't matter. We want to integrate to add and get all this. From y to 0, because this is y equals to 0. And that's y equals to y. So when that happens, you go from y to 0, and then this negative mg from y to 0, dy. So negative mg times negative y, mgy. So if I call this the height, then you can also write it down as mgh. That's why the equation for potential energy that you will find in textbooks, the simplified equation is mgh. All right, where h is the height respect to the reference. So that's important about potential energy. You need a reference point or reference frame. So if the ground is your reference frame and the mass is at certain height above the ground, the potential energy is positive. And mathematically, we prove it like this. All right. So again, the potential energy is always the energy stored in a body, in this case, is stored by the force of gravity. The more you lift an object, the more potential energy it will have. All right? And then we have the other form of energy, which is the elastic potential energy. You see, another device that we can use in mechanics, besides pulleys and rods and masses, are springs. All right? And you're going to do an experiment on that called Hooke's law. You see, if you have a spring and you may attach it vertically, the mass will stretch the spring. So you can either stretch it or compress it. That is the value x. The spring may have a natural length, L. And then if you pull it downwards, or if you push it, you are compressing it or stretching it. So negative kx is Hooke's law. This is known as the restoring force. You see, if I pull the mass to the right, there is a force towards the left trying to bring the mass back. That's the restoring force. That's Hooke's law. So we plug that in the work equation and we get this equation for work. This is basically potential elastic energy. Why potential? Because the energy is stored in the spring. And why elastic? Because the spring is considered to be elastic. And that's because of the behavior. The more mass you add, or the more force, the more the value of x. And the proportional constant is k. K is the constant of the spring. Okay? So we're going to do problems using springs, using masses, right? And we might go back to inclined planes, and of course, different situations for work and energy. So now you can see, at least mathematically, how we can relate work and energy, right? Work, energy, work, energy. All right? So we're going to talk about the work energy theorem for sure. But now let's do a few examples using our definition of work that we were talking about yesterday. All right? And there are different situations. You can have a situation like that. That's easy. Let's actually focus on one where you have a force at an angle or on inclined planes. And let's also introduce the work by friction, of course. Right? Okay. There it is. So a situation, an example of work could be the following. So you have on the horizontal, mass, and this mass is of 3 kilograms, which is going to move a distance of 2.5 meters. okay? In a frictionless ground, so no friction, the force acting here is like this. This force is of 20 newtons, and the angle here is of 30 degrees. Okay, so no friction, so mu is 0. They're asking, or you can be asked, what's the work by the applied force? So our definition of work, the general definition of work, is force times displacement. In this case, it can just be the distance times the cosine of theta, where this theta is this angle here. Okay? So we just use that to find the work by the applied force. So the work is 20 times 2.50 times cosine of 30. So this will be 50 cosine of 30. So that's 25 root 3, which gives you 43 joules. If I round it to just 2 sig figs, 43 joules. Okay, that's easy. All right, positive work because it's going to the right, so there you have it. All right, using the definition, that's how you find the work by the applied force. Now, they can also ask you, what's the work by the normal and what's the work by the force of gravity? Okay, so B. What's the work by the normal force? So the normal force, as you remember, is this. But the normal is perpendicular to the ground. So there are two ways that you can think about this. The normal is not producing any work because the mass is moving horizontally. So the work by the normal is 0. The work by the normal force is 0 joules. The other way you can think about it is by using this. Normal times this, cosine of theta, cosine of 90 is 0, so 0. The same about the force of gravity. What about the work done by gravity? What's the force of gravity? Well, what's the force of gravity? mg. But again, mg is also perpendicular. So the work done by gravity is 0 joules. All right? And then what's the work by the net force acting on the block? What's the work by the net force? Well, if there was friction, that would be a more interesting question. But there's no friction, so the net force, right? We did this yesterday in an example. This force, you can draw this component and this component. This is Fx, Fy. But we already know that vertically there is no work. So don't worry about normal or Fy, just Fx. But wait, Fx is this, 20 cosine. So the work by the net force is F cosine 30 times the distance, which is the same as this. So it's 40 joules. All right? That's a very easy example to review the concept of work because it's just horizontal. Now, let's do an example using a different situation. And let's introduce friction. All right? There was no friction here, so that made the problem easy. Okay? So what happens if we introduce friction? Not like that. I want to change the problem. I want to make it now on an incline. Okay? But remember, definition of work, or you can think it like that. You break the force into components, force times the distance, the x component of the force, because that's the one that is pushing the mass to the right. Okay? So, again, we still talk about normal, we still talk about net forces, and now we want to talk about friction. So, sort of like a good review of what we did before. So now let's go and do an inclined plane situation. So you have an inclined plane. Like that, 30 degrees. And you have a mass at rest. So the initial 0. And is sliding down 3 meters. So let's say that all of this is 3 meters. And there is friction here. So the friction is due to a mu k of 0.42. And there are also a few questions. You're going to first find the work done by gravity. So let's start with that. Okay, so you see over there was 0, right? So what's the work done by gravity? So gravity is always acting downwards. So on here, my force of gravity, the weight, it's like this. And the mass is gonna go from here to here. So you are thinking, well, to find the work done by gravity, you need to know, you can think in two ways. How much vertically the block moves from position A to position B. How much did it move vertically? You want to look for this distance. And you are given the hypotenuse and the angle. So this wow, let's call it H. This H is 3 sine 30, which is 1.5, or 3.0, right? 1.5 meters. So the work done by gravity, is the force mg times 1.5. Now, what's the mass? The mass is 4 kilograms. So put here, m is 4.0 kilograms. So this will be 4 times 9.8 times 1.5. 58.8, which approximately 59 joules. There you are. That's what you can think about. That's how I learned it. Now, what's another way you can think about this? Okay? The force of gravity in the mass. So the mass is like this. And it's moving on a slanted distance of 3.0 meters. Now there's the distance. This is the force, mg. And the angle here is 30 degrees. Because this is a right triangle, this is 60 degrees. So you could very well say that the work is mg times the distance 3. So let's call it mg times the distance times the cosine of the angle in between. Let's do it. We should get the same. So mg, this is 4 times 9.8 times 3 times the cosine of 60, that's 1/2. To 58.8, which is again rounded to 59. Two methods that you can use. Right? You find the angle in between the force and the distance traveled, and you use the definition f d cosine. Or you can think it like this, right? The force of gravity is moving the body from point A to point B vertically this distance. So I do that. Two methods. You can pick any. But the take from this problem is that the force of gravity is not, it's not zero. All right? Why is it not zero? Because it's moving horizontally and vertically. That's why. That brings to the next problem, the next question. Oh, there a question? Oh, I thought it was. Okay. That brings to the next question. What's the work done by friction? And you're gonna need that, okay? You're gonna see when we start doing the energy problems. What's the work done by friction from point A to point B? That's why you need to do your forces, your free body diagram. So I want to erase that. I want to leave that in there. All right. So for any of the works, it's always a good idea to draw the force. So the work done by friction, you want to draw the force of friction. The force of friction, if it's going down, is this. Let's call it Fk. That's the force of friction. And because it's opposite to the motion from A to B, it's going to be negative. All right? Now, this still moves from A to B a distance of 3 meters. So the work done by friction is negative force of friction times 3. So it's just about finding F of K. And that you should know, right? That is mu K times normal. Mu K is that. What's the normal? Well, this should be clear by now. Mg sine of theta, and this will be mg cosine. And of course, normal. So the normal is mg cosine theta. So now let's plug the numbers. Fk is 0.42 times mass 4 kilograms, gravity cosine of 30. All right? Oh, wait. So let's see. So 0.42 times mg times cosine 30, 14.2, force of about 14. Well, let's put 4.2 newtons. All right? So that's my friction. So what's the work? So the work by friction, Fk, is negative the force of friction times the distance traveled, 3.0. That will be negative 52.6, which you can round to negative 53 joules. There you are. That's the work done by friction. How important is that you know all this, right? Chapter 4, forces. Okay, so it's a good review if you think about it of what we did before and now introducing the new concept of work. There's another question though, but is it clear? Do you guys, does anybody have a question about this?
How did you get the normal force again? Or mg cosine theta?
The normal force is the decomposition of the weight using the angle theta here. So if that's the angle theta and that's mg, that's the adjacent. So mg cosine, this is the opposite mg sine. That's how you break the weight into components on an inclined plane.
Okay, got it. Thank you.
Now, the final question is an easy one. What's the work by the normal? What's the work done by the normal force? This force. What's the work done by N? Nobody? The normal makes 90 degrees with the distance, with the inclined plane. Because the normal and the distance traveled are perpendicular, the work by the normal force is just zero. That's definition. Okay?
One more question. Why was the work done for friction negative? Can you explain that one more time, please?
The work done by friction is negative because of two reasons. Friction is a non-conservative force,
Oh
which
yes,
we're
you
gonna talk
told
about
yeah,
that.
you said that yesterday.
And also because it's opposite to the motion. The friction is opposite to the direction
Okay.
of motion.
All right, makes sense.
That's why.
Thank you.
Okay. So those are the examples I wanted to go over on that. Now let's talk about conservation of energy, but conservation and non-conservation. There. So one concept that we're gonna introduce right now is the whole idea of conservation of energy. And this can only be introduced by the idea of conservative and non-conservative forces. A conservative force, like gravity, is one where the work is stored in the form of energy and can be released as kinetic energy at a later time. Gravity is a good example. A non-conservative force is friction. The other way you can think about it is friction reduces the amount of energy in any body, in any object, while gravity actually keeps it. The best example is going to be when I show you the mass dropping from a certain height. Okay, if you have a mass at some height, there is some potential energy, mgh. I just show you that today at the beginning of class. Now, when the mass is dropped, you know from kinematics, it's gonna gain some speed. Now, where is that speed coming from? You know that is because of the acceleration of gravity. In this chapter, you can also think about it as energy. The potential energy at the beginning is transferred or is converted into kinetic as the mass is dropped and reaches the ground. Additionally, the work done by a conservative force moving in a path is zero. That's not true for non-conservative forces. Okay, what's an example of a closed path? The orbit of planets, right? The force between the Earth and the Sun, we call it the gravitational force. We're going to study that in chapter 7, all right? Is acting between both, according to Newton. And as the Earth goes around the Sun, the energy is conserved because the net work done by that force is zero. It's in a closed path. And that's important because thanks to that, we can actually figure it out the physics of orbit of planets, which is what you're going to learn as well in this course. The work done by gravity, there it is, right? The work done by gravity on a closed path is zero. All right? You see that there? mgh, zero. If you go from A to B, the work done by gravity is zero because, like I explained in the example right here, mg and the path AB are perpendicular. So there is no work. From AB and CD, there is no work. It's zero. Now, what about DA and BC? Well, if you're going down, mgh. If you're going up, it's negative mgh. So mgh plus or minus mgh is zero. Now, why is it negative here? Because you're going from B to C. It does depend on the reference. If I make my reference AB, then the work here is positive because you're above the reference. If your reference is DC and you're below the reference point, your potential energy is zero. That's the convention. All right? So if you're above the reference line, your potential energy is zero, is positive. If you are below, your potential energy is negative. And that comes with the math, right? If you have done integrals, it has to do with the limits from 0 to y or from y to 0. It's just that, okay? That's mathematically. Physically, it's just that if you're above, it's positive, if you're below, it's negative. It's just the convention. Additionally, the work done by a conservative force is independent on path. That can be explained by the physics behind ramps. You see in the ramp I show you here, I mean in that one there. What if it was like this, as a curve? You're gonna learn that if the ramp is straight, or if it's like a parabola, because the only force acting is the force of gravity. We are ignoring friction, by the way, okay? If the only force is gravity, the work done between initial position and final position is independent on the path. All right? So basically, if you know the energy at the beginning and the energy at the end, the energy is conserved. It doesn't matter if it's straight or in a sort of loop. Okay? That is the idea of conservative forces and the idea behind work by a conservative force being independent on the path or trajectory of the mass. All right? So there it is, right? If you pick a ball and you place it on a shelf, you are doing work on the ball because the ball now is on top of a shelf. So then there is potential energy stored by the ball and you get it back when the ball is dropped. But that potential energy doesn't disappear. It's converted into kinetic energy. That is the idea here. So when you place a mass on top of a shelf or when you lift it, you are increasing the potential energy and decreasing the kinetic energy. The addition of potential and kinetic energy, so what you have in there, U is a variable that in physics is used a lot for potential energy. Okay? You may have UG or UE later in physics too. Sometimes to make it easier, I just put P, potential energy, and here KE. But the way you read this is that the mechanical energy is the addition of potential plus kinetic. And if the work is only done by conservative forces, the final energy is equal to the initial energy. Basically, the conservation of energy. Okay? This is applied a lot for objects that are being dropped, like on the air. I gave the example yesterday of roller coasters, but the thing about roller coasters or ramps is that this only works if we ignore friction. If we cannot ignore friction, then we have to introduce the work done by friction, which is going to be an expansion of this. All right? So for now, we're ignoring friction, although you already know how to calculate the work done by friction. Okay? Now, why the work done by friction is negative? Because if you have friction, the energy at the beginning is more than the energy at the end. And where did that energy go? By the work done by friction. So energy at the beginning minus the work done by friction is the energy final. That's why the work done by friction is characterized with a negative sign. Okay? Because it's opposite to the motion of the mass or the object. Okay, so yeah, conservation of energy can make some of the problems that we did in the past more easy to or easier to be solved. All right, let's actually show you. Here they're showing you an object that is being dropped from rest. We did that problem using kinematics. Now let's do that problem using energy. All right, you can also have springs like that. All right, you can also solve problems using springs. All right, so for example, here I place a mass at rest. I let it go, and the spring is gonna extend. By extending, there is potential elastic, but that potential elastic is transferred to the mass as kinetic energy there. And then if the mass is released from the spring, think about it, right? Like you have a spring, you compress it, there's potential elastic, you let it go, the mass speeds up, kinetic energy, and then when the mass goes all the way up and it stops, there's no more kinetic energy. So where did it go? Into potential energy. Okay? So those are examples of conservation of energy. So let's do that. All right. So again, be careful with some of the notation that the book uses. All right. W for work, U for potential energy. I might use P, as I said, and K for kinetic energy. Please, the way I'm going to use KE because there's also K here. So what's the K there? Lowercase k, is the constant of the spring. So this is a spring that I was talking to you guys about in the beginning of class. Any spring has a constant k and an elongation x when you extend it or compress it. So 1/2 kx squared is your elastic potential energy or potential elastic energy. All right. And that's what you can use for this, for example. All right, so let's do a few problems using conservation of energy, which, by the way, is going to be in the exam. All right. So the example that was in the slide. You have the ground, you have a mass, and initial speed is 0, so it's at rest, and it's being dropped. Let's call this h. Look, I don't give you the mass. Initial, I want to give you the height though. The height is 20 meters. You want to find the speed when it reaches the ground. If that's from rest, what's VF? All right, so how do we use conservation of energy for a very simple example or situation like that? First of all, the ground is going to be my reference point. I need to do that first. If that's my reference, then the mass at rest has potential energy. The potential energy is mgh, this h. And when the mass reaches the reference point, at the reference line or point, the potential energy, P, is 0 joules, but it gains kinetic energy, K. So energy initial is equal to energy final. Energy initial equals to energy final. What's energy initial? mgh, mass times gravity times height. What's energy final? Kinetic energy. 1/2 mv final squared. You don't need a mass because the mass cancels. The height is 20. Okay. 9.8 times 20.0, 20 is equal to BF squared divided by 2. This 2 goes here. So 2 times gravity times 20, that's B final squared. So that's how I find my B final is the square root of 392, which gives me 19.8 meters per second. That's conservation of energy. All right. Why can I apply conservation of energy? Because the only force acting is a force of gravity. And the force of gravity is a conservative force. Right? The only force acting is mg. That's the one. Okay? All right, let's do now a more interesting example now. This one is just to show you how it works. So what applications can you have? Let's do the roller coaster. All right. Now for that, we're gonna ignore friction, all right? And then we'll do and then we're gonna introduce friction again. For now, let's ignore friction. So an example will be that. Okay. You have a mass M. Let's make H 10 meters. And this 15 meters. Wait. Or not. Won't work. Let's just make sure this works. There, that will work. So let's just change this. H2 8 meters. Yeah. Point A, point B, point C. So ignoring friction, what is the speed at B and at C? That's a classic example of conservation of energy. Oh. So you're going from A to B to C. Like that. How do you find the speed here and here? So, because we're ignoring friction, and the only force acting is the force of gravity, okay, then we can say that the energy is conserved. So energy at A is equal, the mechanical energy at A is equal to the mechanical energy at B equal to the mechanical energy at C, right? E is the mechanical energy, which is potential plus kinetic. Additionally, I'm going to set my reference on the ground. So here is my point of reference. So the mass is going to be here. Let's call it V1. And then here, V2. V1, V2. How do I find the speed at V? Just like we did a previous example. Energy at A, oh, this is at rest. Since that's the reference line and the mass started at point A, At point A, you only have potential energy. So the energy at A is mgh1. And the energy at B, because it's on the ground, is just kinetic, pure kinetic, 1/2 mv v1 squared. So we're gonna set them equal to each other. Like before, mass drops. V1 is 2gh1 square root. Square root 2 times gravity times 10. That's about 14 point something. Yeah, it's 14 exactly. 14 meters per second. All right? That's on B because that's on the ground. What about on C though? C is now at some height. Energy at A is equal to energy at C. So energy at A is equal to the mechanical energy at C. Energy at A is mg h1. What's the mechanical energy at C? There is some height, which is 8 meters. So potential plus kinetic. mgh2 plus 1/2 mv2 square. Potential plus kinetic. Now, something nice about these problems is that mass is cancelled. So at the end, you just have gh1 minus gh2 equals to 1/2 v2 square. So, okay. 2 parentheses 9.8 times 10 minus 9.8 times 8. That's equal to v2 squared. And then I take the square root on both sides. So let's see what I get. So we can just factorize 9.8. So it's 2 times 2 times 9.8. 6.3 meters per second. So if you do the math, V2 is 6.3 meters per second, which makes perfect sense. It's less speed because you are at some height. The energy is conserved. It's just that you have some potential now. You are gaining some potential, which is lowering the speed. I believe there's a problem like this in the assignment, where you have to do this. All right. If you ignore friction, it's not bad. All right. If you ignore friction, the problems are actually easy to solve. Let's now use springs. All right. Let's use it horizontally or vertically. Yeah, vertically. The example that you guys had in the thing. All right. Because this is just potential due to gravity, mgh, and kinetic. Let's combine the free of the free form of force, the free form of energy. All right. Like that. So you have on the ground, you have a spring attached to a plank, like to a wooden plank like this. There, that's your spring. And when you place a mass, so exactly doing it like this. Five kilograms. Is pressing towards the spring. So the spring should be here, but is compressed at distance y or x, because that's the compression of the spring. Yeah, I mean, it doesn't matter if I put 80 centimeters. The spring has a constant K of 200 newtons per meter. Those are the units for the constant. So you're given that. You're gonna let it go. So when you let go, you're gonna have this. The spring is gonna go back to where it should be. The mass will gain some speed, V, right? And then, so this is like that, and then what happens at the end, logically, the spring is still here, so this is there. The mass will fly up until it reaches a height. V0, V5. You want to find this height. Let's call this H. So that's the situation there. All right. You place a mass, you let it go, it goes, it's a stretch, this gains some speed, the mass leaves, and then it stops there. So you're gonna find two things. Part A, find the speed of the mass right before leaving the plank. This. Okay? And then, for part B, here, you're gonna find the height it reaches. All right. So, like I said in chapter 4, you need to first understand what's going on before you use the equations and the formulas. The only, well, there are two forces acting here, right? There's Hooke's law that is gonna push this upwards, and then here, or in every situation, the force of gravity. Both of those forces are conservative. So we can apply conservation of energy. There is no friction in this case. All right. Now, to apply conservation of energy in this, at the beginning, when the mass is compressing the spring, there is elastic here. Elastic potential energy is stored in the spring because of this, right? So now you can say the elastic potential energy, right, is 1/2 kx squared. I have k, I have x. I can find the elastic potential energy. When you let it go, the mass will jump. So the potential elastic energy is converted into kinetic energy. Right? Now, let's be more picky about this. You could ignore it, but I'm not gonna, because it's 80 centimeters. The mass was at this level. It went up 80 centimeters, right? Because it was attached to a spring, so it went up. Besides kinetic energy, it also gained some potential energy to gravity. You need to draw a reference here. This dotted line, that's my reference. So there is some potential energy due to that 80, well, it should be here, not there, my bad. It's here. There it is. That's my reference. So there is there's 80 centimeters, so that's 80 centimeters. So this also gives you potential energy due to gravity. And then when the mass leaves the plank, there is potential energy here. All of this, because it stops. So it's just potential energy. So now that you figure it out, you can start solving for the variables. Let's start with V. All right, how do I solve for V? Energy at the beginning is just potential elastic. So I will do 1/2 kx squared. That's the energy here, which is kinetic plus potential. 1/2 mv squared plus mgh. So I have k, is 80 centimeters, so 80 is 0.80, right? So here, Okay. So let's see. 1/2 200 times 0.80 squared is, that's why you need a mass now, because, 1/2 times 5 v squared plus 5 times gravity times what height? This height, 0.80. That goes here. All right, that makes it more interesting. So this is 100 times 0.64. Yeah. That's 5v squared divided by 2 plus that 5 times 9.8 times 0.80. So 5 times 9.8 times 0.80, 39.2. There. So 100 times 0.64, 64. So 64 equals to 2.5 v squared plus 39.2. So I just subtract, right? 64 minus 39.2, that's 24.8. That's 2.5 v squared. So v is this divided by that, square root. So 24.8 over 2.5, square root 3.1 meter per second. There you are. All right, so what did let's recall. Potential elastic is transferring to potential and kinetic. Why is there kinetic? Because it's speed. Why is there potential? Because that's my reference line. The spring was extended. We have to consider that for the... that's easy to ignore. Be careful. If you ignore that, the difference is quite high. You will get about twice as faster. So good.
I have a quick question. Why is it 80 centimeters on both? Like in the first part and the second part?
80 is
X.
X. That's your X here. That's the formula. That's the extension, the compression. And it's also 80 here because you are looking at, so the Planck. So this should be here, I guess, yeah. So the Planck went up 80 centimeters. It was here and it went up 80, all right? So I should have done probably this in here. Yeah, so let's...
Okay, I got you.
So, yeah. So it went up 80 centimeters, that's why. All right? Maybe if I do it like this. There. That's why. All right? Equations
Sorry.
are easy. It's just how you use them. Now, to find H. To find H, because of conservation of energy, the energy here is equal to the energy here. You can just use that. Right? All the energy here that was stored on the spring went up for the mass to reach this level. By the way, of course, we're ignoring the mass of this. No, that's okay. So potential elastic energy equals to the potential energy of all this. mg times the whole height. H plus 80 centimeters. 0.80. All right? You have to take that into consideration. So let's do that. We can do that in here now. So for part B, this one, potential elastic is equal to potential energy at the top. That. So this is this 1/2 of 200 times 0.80 square. Potential energy at the top is m g and what's h plus 0.80. How about that? So yeah, again 164. Right, we got it before there, 64. 49 h plus 0.80. Divide by this, so 64 divided by 49. That's 1.31. 1.31 is h plus 0.80. Subtract 80 is 0.51 meters. In centimeters, that will be 51 centimeters. So half a ruler. The ruler used in class, half of that, like this. Not bad. That's a more complex conservation of energy example. You've seen a roller coaster. That's an easy one because there's no spring. But if you include the spring into the mix, that is a good example. All right. In the book, so I have it here as well, they give you the other way around, and you guys could do that as practice. I think I do that in the video I have in Canvas. Is the, you know how I had the mass and then you're going up? Imagine you have the spring and then you let the mass drop. So it goes. It's the same idea, right? You can do it on the inverse, letting the mass drop. And again, I think I go over that in a video here online I have in Canvas. All right. But does anybody have a question about this?
Yeah, I have a quick question. For part A, when you found the formula to find the speed right before it left the plank, how did you derive that formula? Could you explain that again?
The
The 1/2 kx squared equals 1/2. I know 1/2 kx squared is the potential elastic energy, but that's equal to, how is
kinetic,
that equal to the other two?
that's kinetic, 1/2 mv squared
Okay.
plus mgh, which is the mass times gravity times height. mgh, that's h, mgh.
Okay. And then how do we know to add both of those in order to
Ah.
get the
That's your definition of mechanical energy. So mechanical energy is potential plus kinetic. So in the roller coaster in part C, I added potential mgh plus 1/2 mv squared. So you have to add all the energies that are acting on the mass at a given point.
Okay.
Yeah.
That makes sense. Okay.
Again, that's why before you solve a problem of conservation of energy, you need to think what's going on first on the problem.
I have a quick question. So if the roller coaster had, like, let's say one more hump, well, if we were trying to figure out that, that total energy at the top, would it be all of those energies together, or would it just be the last two?
What do you mean?
Like, you know how you said it's kinetic plus potential? So if
Yeah.
there was one more like hump, for example, would it be
Yeah.
all of the kinetics and potentials of all of the points?
You have to know what's the height of the other hump. If the height of the other hump was 10, then it was 8, let's suppose it was 5. So it will be mg5 plus 1/2 mv squared on that point.
So, okay, so you do just keep adding more and more.
Yeah.
Okay.
Yeah. I will do another one because like similar to that, adding a spring. What I want to do now is I want to give you guys a break of 10 minutes, and then we're going to introduce external forces with energy, all right? And then friction. Okay, so take a 10-minute break. It's 7:27. We come back at 7:37. All right, guys. So let's continue with this section of energy. Now we are going to introduce external forces. All right. Similar to what we had at the beginning with work, you have a 15 kilogram mass on a surface without friction. All right. So no friction here. For now, I want to add it in a bit. So this force is going to increase the speed of the mass because of the acceleration. But you can also understand this as the work done by the external force is equal to the change in mechanical energy. That's just the work energy theory. Now, that makes sense because every form of energy, kinetic, potential, and elastic, we can prove those equations that we use with the equation of work. So yeah, work is basically change of energy. All right. So using that, how can I find the speed after the mass traveled this distance of 10 meters? You know that there is an easy way to find the work done by the force. All right, this. The work done by the force is F the cosine of the angle. How the cosine there? The angle there, sorry. dF. And is the change in mechanical energy. Mechanical energy is potential plus kinetic. At the beginning, and it's on the ground, so there is no potential energy. But at the beginning, it's traveling or is moving at 6 meters per second. And then it's V. So this work is change on kinetic energy only. And I can write this like this. F d cosine theta is 1/2 mass V final square minus 1/2 mv initial square. All right. So we can substitute all the values. I have 90, 10, cosine 60, and then you see here, you can factor 1/2 m, right, on both sides. So I will write this as this. 90 times 10 times cosine of 60 is equal to 1/2 m, 15, v squared minus 6 squared. All right. Cosine 60 is 1/2. So 90 times 10 times cosine 60 is 450. 450 is 1/2 times 15 parentheses v squared minus 36. 450 over 15, that's 30. Yeah, times 2, that's 60. 60 is v squared minus 36. On both sides, that's 96. That's v squared. You take the square root on both sides. That's about 9 point something, right? 9.7 probably. Yeah, 9.8. So there you are. Now you can find the speed of a mass due to an external force by using the work energy theorem. Why you cannot use conservation of energy? Because there's an external force. It's not just gravity acting on it. All right. Furthermore, what happens with friction? So let's change this problem a little bit. I'm going to remove the force. I'm going to add friction, and let's see how the work energy theorem works. And that's a non-conservative force. For non-conservative forces, you cannot use a conservation of energy, but you can use that guy. So let's leave this in here, and let's show you. Let's see what is this. Yeah. Again, 10 meters, but it's going to start at, yeah, let's start at 6 meters per second. And then it's going to stop. So it's like it's traveling, and then it's going to stop because there is friction. There is a mu k of 0.25. So the question is, now they can ask you how long, how much it travels. You want to find this when it stops. And you don't have time. You don't know you know what's the force acting on it. There's no other forces but friction, right? That's why it's stopping. So friction is this. So I can still use this, but my change of energy final minus energy initial, is negative. So how does that work? Okay, let's write here. For a non-conservative force, for non-conservative forces like friction, the work done by them is equal to negative change in mechanical energy. All right. So stops. So energy final is 0. Energy initial is kinetic. I need a work done by friction. The work done by friction is the force of friction times the distance d. Friction acts all along. All right. That's why, right? Fk is mu k times normal times the distance, the work. This is mg. This is the normal. So the normal is just mg. So mu k mg times distance. All right, so now let's use that sort of a variation of the work energy theorem. It's the same if you think about it. It's the same. 0 minus 270, that's 270. So that minus that. Right? Is negative, well, negative of that. So negative, or you can do it like this, by the way. 0 minus 270 is negative of this, negative of the work done by friction, right? And that will be 0.25 negative UK times 15 times 9.8 times the distance. You want to find the distance here. There you are. So negative 270 is negative 0.25 times 15 times 9.8 times the distance. Negative and negative ends up dropping. So it's just a sign that you drop. So then distance is 270 divided by 0.25 times 15 times 9.8. All right, let's see what we get. $7.3 meters. So that's how much it traveled before it stops. Look at it. I can find distances and speeds without kinematics, just by using work and energy. Questions? Now you saw the work done by friction, by the way. Right? And the work by friction is negative. Now you can see why the work of friction, why is the work done by friction negative? Because it gives you a negative change on energy. It reduces the amount of energy. That's why. Okay. No questions?
Can you explain again how you got the how you derived the formula for the work of friction?
So the work done by friction is the force of friction times the distance traveled. So this times this, right?
Mm-hmm.
Fk friction is mu k times normal. Mu k is the mu. Normal is this force going up. Since it's just mg and normal like that, normal is mg. So mu k times mg, that's the force of friction. And this is just the distance.
Okay, got it. Thank you.
All right, so now that we have introduced all these concepts, now we can go and do more interesting. Oh no, we can combine sort of what we did. Before I want to do an example with non-conservative forces. There's one that I saw here. Oh, there it is. The bullet problem. Let's go. No more questions? Okay, so let's do a real case. Let's do an application of this work and energy theorem on friction. You're gonna do sort of like, there's a lab about that actually, of the problem I'm gonna do. Not exactly like what we're gonna do, but it's similar. It's a bullet. So an example. So you have a bullet traveling at 580 meters per second. And there is a wooden mass here on a horizontal table. Now that mass is fixed, not gonna move. And the bullet penetrates this mass. So this bullet, let's make it smaller. It penetrates till here. And then, of course, it stops there. And it only goes 6 centimeters. It goes all the way in 6 centimeters. All right. Find the friction inside. So, part A. You want to find the frictional force inside a mass that stop the bullet. All right, that's a classic example of the work energy theorem. All right, so think about it for a second. So anybody have an idea what to do? Think in terms of energy, right? It's the work energy theorem. So like the one that I did. What's the energy at the end? What's the energy at the beginning? And why is it stopping? Why is the bullet stopping inside the mass? Anybody?
Because the frictional force of the mass is greater than
Yeah.
the
You're right. You need a mass of the bullet. The mass of the bullet is I think 8 grams, 7 grams. It's not a lot. It's 8 grams. This is an 8-gram bullet. Yeah, so it's stopping because of the force of friction, right? So what's the energy at the end? What's the energy here?
0.
0. And what's the energy over there at the beginning? What's the initial energy? Hmm? By the way, if you're wondering, it's at the same level, right? So no potential energy, no gravity, no, right? Pure kinetic, right? It's just only kinetic because of the speed. So 0 energy minus kinetic by conservation of energy, there's nothing here. So the energy here is the energy here. When the bullet is entering the mass here, we're going to assume that it's still 580, okay? Constant. So 0 minus kinetic energy is equal to the work done by friction. Well, negative that work. You want the frictional force. What's the distance traveled? 6. That's it. That's what you have to do. So you could write that the work by friction, negative the work done by friction, is the change of mechanical energy, which in that case is just kinetic energy. So negative the frictional force times the distance, 6, but 6 centimeters is 0.06. That's equal to energy final minus energy initial 1/2. What's the mass? 8 grams. 8 grams is 8 divided by 1,000, 0.008 times 580 squared. So the negatives are gonna be dropped. So Fk, you want this, times 0.06 is 1/2 0.008 times 580 squared. There you are. That's how you do it. So Fk is 0.008 times 580 squared divided by, you multiply this to 0.12. All right. It's gonna be a lot. You're stopping that bullet. Yeah. 22,427. I'm rounding it to a whole number. Not good. Newtons is a force. Any questions? There's one more. Huh? I just saw in there. They asked you for one more thing in there. Makes sense. It has to be a huge amount to stop a bullet. So yeah. Be careful with the units, right? Grams to kilograms, centimeters to meters. Very important. So what's part B? Assuming a constant force. So assuming that's constant. Which, yeah, I guess you can assume. Assuming a constant force. How long it took the bullet to stop? So find that time. Find the time it took for the bullet to stop. How will you do that?
Could we use Vf is equal to Vi times Bi plus acceleration in time?
Yeah, so you need to find the acceleration, right?
Yes.
Yeah, so let's do that. You have the only force acting on the bullet inside the mass is that, right? Let me just double check this. Yeah. Is that. So we can find the acceleration. We can find the deceleration because this is slowing down to zero. From there to zero. How will you find the acceleration, by the way? If that's the only force acting on the mass. So we're ready. That's part A. Or part B. how will you find the acceleration?
We find the net force and divide it by the mass.
Yeah. So force equals to mass times acceleration. The force is that, no, it's the negative force. So negative, well, this is just a magnitude for now. 22,427 is the mass of the bullet, 0.008 times acceleration. So your acceleration towards the left is huge.
2,803,333 meters per second squared.
75, right? You have here 2,803,375. So then I can use the equation B final is V initial plus or minus A delta T. B final is 0 because it stops. V initial is 580 minus that acceleration times delta T. So I get time is 580, 2 million. So let's see. So I'm gonna get 2.1 times 10 to the negative 4 seconds. They want you to find the time in milliseconds. To do that in milliseconds, you multiply by 1,000. So that will be 2.1 times 10 to the negative 4 times 1,000 milliseconds. That will be 10 to the negative 4, 10 to the negative 10 to the 3, 10 to the negative 1, 0.21 milliseconds, which makes sense, huh? Makes sense. Think about it. A bullet. 0.21 milliseconds. So kinematics, huh? Yeah, that's why. So the thing about physics is that everything is connected. We can go back to what we did in chapter 2, chapter 3, right? We use a lot of forces and, normal and all that. Questions about this? There are a couple of problems that's from the textbook, all right? And I believe in the assignment 5, there is a problem like that as well, similar at least. Yeah, it's here. That problem with the mass and the hook and the spring is in the assignment, huh? So now you can do it. The one that we did in class. Okay, guys, let's combine both now. Because we can do that. We can combine this and conservation of energy. That's what I wanted to get today as well. And honestly, I'm gonna do at least tomorrow. So it's 8:10. We're probably gonna finish a bit earlier today, because the topic builds from what we did before. So if you already know forces and kinematics, then energy and work are extra stuff. All right. The same is gonna happen with chapter 6 when we introduce momentum. Okay. We're still gonna be talking about forces and so that's the thing about physics. If you know the previous topics, then it gets easier and easier, all right? So yeah, let's combine this and conservation of energy, all right? No questions about this? We'll see. I'm gonna let you guys try the next problem, okay? I'm gonna combine quite a few things in there. So let's see if you understood. The only thing that you guys need to know are definition of work, your equations of energy, and let's see if you understand conservation of energy and work energy theory. Okay. So we have a slide with no friction, like this. And then it reaches a path with friction. And then it continues without friction. Until it reaches a spring. There. All right. Let's say the mass is here. M at rest. So that's at rest. No friction here. You have point A, point B, point C, and here, point D. Why you have all those points? Okay. So this is a spring with K equals to 100 newtons per meter. Okay. And here in this blue section, there is mu 0.2. All right. So part A, find the speed of the mass at B. So let's give you the height. So this height is of 30 meters. So 30 meters, you're gonna find that. You need this, BC. Let's say that's only 10 meters. You have mu, yeah? So part B, find the speed at C. Find the speed here, find the speed here, and then calculate how much the spring is compressed. Okay, so let's explain this. You have a mass, and you need a mass at some point. So let's give you the mass Let's make it 4 kilograms, all right? So gravity and M, let's make it 4 kilos. So you have a 30 mass of 40 kilograms. At rest, it's gonna drop without friction. It reaches this point, so you can find the speed at this point. Then it's gonna enter this rough, it's friction here for 10 meters. And then it's gonna continue with no friction, so there's no friction here. I should leave it with friction, but anyway, let's leave it like that. No friction, and then it's gonna stop. So then it's gonna stop at D. So the mass reaches this point and it stops. Stops there by compressing the spring some distance x. You want to find that in here. How much the spring is compressed. And then, of course, you want to find V here and V here. All right. It's a nice combination of everything we've done. Well, that's it. I'll give you some time to do it. Anybody got the speed at B?
You asked for the one at B, right?
Yeah, what is it?
I
What
got 24.2.
Yeah, good. Do you find the one at C?
No, I didn't get there yet.
That's okay. I'll let you guys keep working. Should have put more distance there. It reduces, but not by a lot. Ooh, heat wave. So anybody found the speed at C? What do you have to do between, what do you have to use between B and C? If there is friction in there.
The force of friction.
Why? What does the force of friction do? What does it do? Hmm?
It
Slows
decreases the
down.
velocity.
It decreases the velocity by decreasing the energy. Why? How do you compute that? What does the, how do you use the force of friction? In other words, what do you use? What concept that we covered today do you use? Because from A to B is conservation of energy, no friction. From B and C, what do you use?
Kinetic energy?
You use kinetic energy, but what concept? What concept that we covered today do you use?
Non-conservative forces.
Yeah, you have to use the whole work by non-conservative force, which is the friction. That's why, okay? The work energy theorem. And between C and D, there's no friction. So once you find the speed at C, you can use that to find the X value, the compression. All right, so I think B should be clear for everybody. So what do you guys do to find the speed at B? B1, part A. What do you guys do?
I set up EA is equal to EB, so MGH is equal to half M, the velocity of B squared.
Yeah, very good. Mechanical energy at A is equal to mechanical energy at B because it's conservation of energy, no friction. So yeah, because it's at rest, MGH, yeah, MGH equals to kinetic. B is just kinetic. This is my reference, right? The ground. So 1/2 mv squared, B1 squared. So mass cancels, we did that before. So yeah, V1 is just the square root of 2 times 9.8 times 30. That's 24 point what?
5.
0.2.
Let me double check that.
Wait, it is 2.
24.2, yeah, meters per second. All right. Okay, did anybody do B? The speed at C? What happens between B and C? There is friction. So you have to use the work done by friction, or negative the work done by friction, is the change on mechanical energy. Okay, guys. You guys should tell me, what's Fk for this? Or tell me everything. What's the work done by friction? Here. Hmm?
Mu of K times the normal force times the distance.
Very good. Mu K times the normal force times the distance, which is T. That's delta T. Okay. Mu K is 0.2. What's the normal? What's the normal for this? This is easy. What is it?
Mass times gravity.
Yeah. Mg normal. So yeah. Mass times gravity. Mass is 4. Gravity is 9.8. Distance is D. And what's delta E? Energy on C minus energy on B. Energy on C minus, what's the energy on B? 1/2 mv squared. That's where you find this. There you are. Right? So, let's see. 0.2 times 4 times 9.8 times 10. That's 78 point, negative 78.4. So, all this will be negative 78.4. is the energy on C minus this. 1/2 4 times 24.2 squared, 1,171.28. So the energy on C is that minus that. $1,092.88. Yeah. But what's the energy on C? It's just kinetic. So that's 1/2 mass V2 squared. There you are. How about that? There. So if I solve for that, right? I get 23.4. So it gets reduced, not by a lot, almost by 1 meter per second, but it gets reduced. All right, guys, do you guys have questions about this? It's different, right? That was just conservation. That's easy. Here you have to take into consideration the work done by friction and the change on energy. Energy changes because of the work done by friction. There you have it. Okay?
That change of energy, I'm sorry, is just from point B, right?
From C to B.
To B. Okay, thank you.
Energy on C minus energy on B. Yeah. We are not done yet, but is that clear? So the speed here is 23.4. And now, again, without friction, it's gonna compress this spring. How much? How do you do that? Let's see if you understood the spring thinking. How do you do part C? How do you find how much the spring is compressed? By when the mass hits and then keeps trying to, and it stops, right?
Do you set up the elastic potential energy with the sum of the kinetic and the potential for the whole thing?
Yeah, but what's the potential there?
It stops, so 0.
The potential is 0.
Yeah.
And the kinetic, sorry, at this point, kinetic potential is 0, but there is potential elastic.
Okay.
Right before the mass hits the spring, what's the energy here? What's the energy here, right at this instant?
Is it 1,092.88?
Yeah, is the energy, is the kinetic energy. It's 1,092.8. Very good. So kinetic energy is 1/2 kx squared. But that energy, we found it before, right? 1,092.88. So 1,092.88 is 1/2 k x squared. And you solve for x. Okay, you guys do the math. How much you get for x? I mean, I already did it, so I know how much it is. So what do you get for x?
4.7.
Yes, that's the answer. Meters. So yeah, there you are. That's basically chapter 5. We have one extra class tomorrow, so I will go and do just examples. Like I did before. You guys are gonna do this today. We have time, but I'm gonna stop today's class. Let's just stop it now with the recording.